Geometry, thanks for tuning in for another episode of Math with Mullins. Today we're looking at lesson 9.1, the Pythagorean Theorem, and we're just going to be able to tell what the Pythagorean Theorem is, be able to use it and the converse, and then classify those triangles. Sorry, you're going to hear some bells here for the first minute or so. The first thing we're going to look at is Theorem 9.1, which is the Pythagorean Theorem. You can use it in a right triangle. The square of the length of the hypotenuse is equal to the sum of the squares of the lengths of legs, or a squared plus b squared is equal to c squared. Pythagorean triples is the next thing we're going to see in our notes. That is a set of three positive integers, a, b, and c, that satisfy the equation for the Pythagorean theorem. Common triples are 3, 4, and 5, 5, 12, and 13, 8, 15, and 17, and 7, 24, and 25. Essentially what these examples down below it mean is those are just multiples of those triples. So like 6, 8, and 10 has been doubled, 9, 12, and 15 has been tripled, and so forth. Okay? So what we're going to do is just find the value of x here, solving it, and then tell if it forms a Pythagorean triple. So the first one, we have 6 squared plus 4 squared is equal to x squared. This will be 36 plus 16 is equal to x squared. 36 plus 16 is 52. And one thing we're going to see in chapter 9 is a lot of non-perfect squares, and we're going to start to simplify the radical. So we do want to find the square root of 52, but 52 is not a perfect square, but the number 4 can go into 52. So this would be the square root of 4 times the square root of 13, and then I can simplify the square root of 4 to just be 2 square root 13, okay? This one is not going to be a triple, so we're going to say no for the first one, okay? The second one I have is x squared plus 3 squared is equal to 5 squared. This one is looking like a common one that we're going to see. If I solve for a, I'm going to get x squared is equal to 16, so that square root would give us 4, and this one is a yes common triple. Okay, the next one also looks like a common one. 5 squared plus 12 squared equals x squared. We're going to get 25 plus 144 equals x squared. 25 plus 144 is 169. And then when we find that square root, we get 13. So this one is a popular triple. Okay. Then our last one, we've got 7 squared plus x squared is equal to 14 squared. We've got 49 plus x squared is equal to 14 squared. That would be our 196. Then we're just going to subtract 49 from both sides there to get 147. Okay, and then we just want to think, are there any perfect squares that can go into 147? We can maybe try 49. Yep, 49. If I do the square root of 49 and the square root of 3, but square root of 49 would be 7, keep the square root of 3. So this one would be a no, because we're not using those triples. In order for that one to work, we would have to have completely different numbers. So the next one we have is a flagpole shown supported by 2 wires. Use the Pythagorean theorem to approximate the length of each wire. So what we do know is down below we're seeing 2 right triangles. So what I would do here is I would just use 8.5 as a leg, square it, plus 15.1 since it's representing that pole, and then is equal to x squared, which is our hypotenuse. So we're going to do our 8.5 squared first. We're going to get 72.25 plus 15.1 squared is 228.01. Let's add those together. So plus 72.25, we get 300.26. And then I'm going to go ahead and find the square root because it does say to approximate, so we want a decimal format of that. we're going to get a long decimal, so let's just round it to about 17.3 feet. Okay, next up we got a new theorem here, so we can grab our theorem sheet. The converse of the Pythagorean theorem just states if the square of the length of the longest side, which is your hypotenuse, is equal to the sum of the sides of the lengths of the other two sides, then the triangle is a right triangle. So if we can use a squared plus b squared equals c squared, then we can prove it's a right triangle. So we're going to try that in these two. So this would be a, b, and we're assuming this could be c. So 9 squared plus 15 squared is equal to 3 square root 34 squared. Okay, 9 squared is 81, 15 squared is 225, and then when we square this, everything in here gets squared. So this 3 squared would be a 9, and then the square root of 34 squared is just 34. We're going to multiply that together. 9 times 34 is 306, and then over here, 81 plus 225 is also 306. So we could say, yes, this does form a right triangle. Here I'm going to use this as AB and my biggest side C. So 14 squared plus 22 squared equals 26 squared. I'm going to start with our 26 squared. That is 676. Then 22 squared, 484. And then our 14 squared is 196. So we just want to know, is 484 plus 196 equal to 676? And it is not. 680 does not equal 676, so we got to say no for that second example. Okay. Our third and final theorem we're going to talk about is our Pythagorean Theorem inequalities. For any triangle ABC where C is the length of the longest side, the following statements are true. If C squared is less than A squared plus B squared, then it is acute. But if C squared is greater than A squared plus B squared, then triangle ABC would be obtuse. So basically we just want to say if C squared is smaller than the sum of A and B squared, then it's acute. If C squared is larger than the sum of A squared plus B squared, then we would say it's obtuse. Okay? So what we're going to do is say verify that segments of the lengths of 3, 4, and 6 form a triangle. So is 3 squared plus 4 squared equal to 6 squared? So 9 plus 16, does that equal to 36? No, it does not. Oh, sorry. Does it form a triangle? Not a right triangle. So this is where we're going to use our lengths, like 3 plus 4 greater than 6. Yes. So yes, it can be a triangle. But now we just want to see, could that be acute, right, or obtuse? I know it's not right because I just tried to do the 3 squared plus 4 squared equals 6 squared. It doesn't equal 6 squared, but 3 squared is 9, 4 squared is 16, and we're going to see how big it is compared to 36. 9 plus 16 is 25, and 25 is less than 36. So since C is bigger, we're going to say this is obtuse. Okay, according to this right here. So the next one, maybe you give this a chance to try it. So click pause when you're done trying it, click play. Here we go. 2.1 plus 2.8 has to be greater than 3.5 to first make a triangle. 2.1 plus 2.8 is 4.9. 4.9 is greater than 3.5, so yes, it's a triangle. So now we got to see, is 2.1 squared plus 2.8 squared something compared to 3.5 squared? 2.1 squared is 4.41. 2.8 squared is 7.84. And then this box is for my comparison later. 3.5 squared, 12.25. If I add 7.84 to 4.41, I'm going to get 12.125, and since it's equal to 12.125, we can consider this a right triangle because it satisfies the Pythagorean theorem. Our last one here segments 14, 15, and 11. I'm going to take my two smallest ones. 11 plus 14 is greater than 15, so yes, it's a triangle. So now I want to see what is 11 squared plus 14 squared, and how does that compare to 15 squared? 11 squared is 121, 14 squared is 196, 15 squared is 225. So 121 plus 196 is 317. So since 317 is greater than 225, we would say this is acute, since c squared is small or smaller. Okay, that'll conclude our notes on 9.1. Hopefully this video helped you. If it did, give it a thumbs up. Thank you so much for tuning in. Next time we will talk about lesson 9.2, which is special right triangles. Have a great day.